Right. In the last video, when I was going through this checklist here, I separated them into what I realised I identified that there were two main topics and then this one outlier here. And the stars represent the ones related to forces and motion, and then the little triangles represent the waves questions or waves topics. Then we've got this random other one, which is to do with magnetism. And I've noticed that I suppose you could link it to forces because obviously magnets cause a force. But other than that, it's not really very closely related. And it looks like you only need to know this one fact. And so just remember iron, nickel, and steel. Actually, there is another one they've not mentioned, I just realised, which is cobalt. Cobalt also is magnetic. Now, also what I noticed about this list, it's a very strange list, in that it's not all of one topic or anything like this. It's kind of bits and bobs. So I think that the test has already been written, and you could pretty much guarantee there's going to be a question on each one of these things here. So at some point in the test, it's going to ask you about, which is the magnetic material. And you're going to have to notice that you got to know that as iron, nickel, steel, or cobalt are magnetic metals. Iron, nickel, and cobalt are elements. Steel is not an element. Steel is an alloy or a solid mixture of metals, the main one being iron. But so actually the magnetic elements are iron, nickel, and cobalt, but steel is also magnetic. So we're going to focus mainly on waves though in this video. So I'll put a link to my database, and we might have a look at some simulations to get our idea and get our head around some of these things. In fact, I can already think of one or a couple actually, which will help us with this. So I will do that. But let's just go through from the beginning. We've got gamma rays are used for sterilizing medical equipment. Okay, well, there's not much to understand, not much else to say apart from that. Maybe we need to know, what does sterilizing mean? It means killing the microbes, the microorganisms on that medical equipment. We don't want to be cutting somebody open and then putting a load of bacteria inside them. That's not a good idea. And so we use X-rays, we use gamma rays. I think we may be able to use X-rays as well, but they use gamma rays usually to sterilize the medical equipment, in other words, to kill any living organisms on that medical equipment. Why don't they use other methods? Because gamma rays will kill the microorganisms but won't affect the actual equipment itself. So that's why they use that. Gamma and X-rays are used to damage cells by knocking parts off them. This is called ionization. It's kind of an oversimplification, knocking parts off them. What does ionization mean? This is chemistry, isn't it? We heard of ions before. When we know that, so I think maybe I'm going to pause the video and get a few simulations ready to demonstrate some of this. Okay, so I've got a few simulations ready now, and there's a link just there to the where you can collect more of those resources. I'll just click on it now to show you what it looks like. So yeah, if you scroll down, you can see that you can just access all the questions there and so on there. And you can also click on practice questions to view other types of resources. Okay, so let's go down here and have a look what we have. Gamma rays are used for, so we said that one already. Well, that's right, I was going to have a look at ionization. That one's actually not in waves, the idea of ionization, so I'm just going to pause it and get that one as well. Okay, so let's head over to this simulation. You can find this simulation obviously in the link above, but you can also find it in my database on within atomic structure. So let's just build an atom briefly. Just recap this. Let's make lithium, which if it has 3 protons. If it doesn't have 3 protons, it's not lithium. If it has and all lithium atoms have 3 protons. That's kind of the definition of what lithium is. Currently, it says it's an ion. If I give it electrons, eventually it will say it's a neutral atom. And that's because the protons are positive, the electrons are negative. So when they balance, you have a neutral atom, and when they do not balance, you have an ion. If you have too many, you would have a negative ion, and not enough, you would have a positive ion. So what does ionization mean? It means making something an ion. The way it might do that is by knocking off an electron. And so when it says knock off bits of the atom, I feel like that was a bit simplified. Where does it say that? Knocking parts of them. So, okay, say it doesn't even say knocking off parts of the atom, it just says knocking parts of the cell. So remember, obviously everything's made out of, so cells are made out of molecules and atoms, or molecules made out of atoms. And so if you were to ionize an atom, then it will cause chemical reactions to take place, and that would change the structure of the cell or of the molecules, and that would therefore change the structure of the cell, and so on. It becomes a sort of butterfly effect. This can lead to cancer or radiation poisoning, or mutations in unborn fetuses. Anyway, so that's what ionization means, and it's only the high energy electromagnetic waves that are able to ionize. So anything with a higher energy or higher frequency than light can ionize. Ultraviolet, X-rays, and gamma rays. Microwaves cannot ionize. So microwaves are used to carry mobile phone signals. Yeah. So a lot of people there was this sort of there was this kind of scare thing going on about about microwaves in mobile phones, and they thought that, well, if you use a microwave oven to heat up food, then surely it's not a very good idea to put a phone next to your head. It seems to make sense, apart from when you take into account that you can heat it. Well, okay, so the power and the intensity of the microwaves coming from your phone is so incredibly low. It obviously isn't going to cause any damage, and it hasn't caused any damage, has it? So there's nothing to worry about. But it's correct that it is within the same range. So let's just recap what electromagnetic radiation is. First of all, let's look at this scale. It's actually not going up in equal amounts. It's going up in powers of 10. So 1 to 10 to 100. And then we get a different unit. That would be 1,000 nanometers, or 1 micrometer, 10 micrometers. And that would be 100 micrometers, or 0.1 millimeters, and so on. So it's actually increasing in powers of 10. And within this range, we have a tiny little area, a tiny little range, which is the visible light, only between 400 and 750 nanometers. So it really is a very small amount that we're able to detect. But the other types of electromagnetic radiation, they are basically the same as what we can detect. We just can't detect them. So I'm simplifying a little bit, but we would say that they're not light because we can't see them. We've given the name light to electromagnetic radiation that we can detect with our eyes, and within that range, that small range, we can determine different colors, and those different colors are our mind's, our brain's representation of different wavelengths of light within that range. So at the lowest frequency, or the lowest wavelength, I should say, this is wavelength here. At the lowest wavelength, we will see blue or violet, kind of. And then if we go towards the higher end, we'll see red. Okay, but outside of either, if you go higher than that, then we see infrared, and we go lower than that, we see ultraviolet. If you keep going lower again, eventually you get to X-rays. If you go lower again, you would get to gamma rays, but for some reason this simulation doesn't include gamma rays. I'm not quite sure why that is, but they should be on there. They'd be below X-rays. Then, so although this simulation gives you a bit more information, like it shows you that infrared remote control uses a different range to infrared cameras, but it gives you the general idea. It hammers home the message that electromagnetic waves are all the same type of wave as light, all the same type of wave as each other. And you can see that the picture of the wave the wavelength is getting longer as I go up. Over here we can see the frequency is changing to, the frequency is going to be inversely proportional to the to the wavelength. So in other words, I'll put the top here, we have a high wavelength. We would also have a low low frequency. I'm actually controlling this at the same time. So low frequency, high frequency. High frequency also has has a low high frequency also has a high energy as well. So high frequency waves have high energy. I've opened up that twice. Let's go back to this link here. Micros are used to carry mobile phone signals, and they can pass through the atmosphere and reach satellites above the Earth. Okay, so that's why we use microwaves. Yes, I think I remember this. Yes, so radio waves. This makes sense now. So radio waves, I presume, can't pass through the atmosphere, and so what we can do with radio waves, you can bounce it off the atmosphere and get it to go around, follow the curvature of the Earth, and reach other transmitters that might have gone beyond the horizon. So microwaves go outside of the atmosphere to reach satellites and then bounce back in, whereas radio waves can just reflect off the atmosphere to reach the transmitter and the receiver. Okay, so I probably gave you more than enough information for those. Let's have a look at this one now. Okay, so amplitude, we're talking about measuring waves now. This is the next few bits, the rest of it on waves is all to do with the main things about waves which we need to understand. So if we click on this one, this demonstrates it the best for that. I think I will, no, I won't, I'll just use this one. There are other simulations within the waves database, but let's stick with this one. When you play around with this yourself, I would say choose no end. I'll explain why in a moment. And then you want to choose oscillate. And we have a wave. Okay. So also what I did is I turned damping off. And when you do A level, then you'll put damping on and you'll notice that what's happening, if I turn it down a little bit more, you can see that the energy is being lost as the wave goes along. Well, we don't really look too much at that at GCSE. So we'll turn damping off. And then what we can do as well is we can put it on slow motion. And first thing you'll notice is it seems as if something is going from left to right, and in fact something is, but not the thing that we think is going from left to right. So if we have to actually look at one of these little circles, in fact, if you look at that green one there, you'll notice it's actually only moving up and down. The oscillation, which is the movement of the particles or the movement of this motor, is moving up and down, whereas the wave itself is going from left to right. So they are perpendicular to each other. They are right angles to each other. So let's use this pen this time. So the oscillation is up and down, and let's write that. Have I given myself enough space? No. Okay, the oscillation is moving up and down, and that should be straight, and it should be a right angle, but it doesn't look like it, but that's supposed to be a right angle. We can call that's the direction of the wave. We can also refer to it as the wave propagation. But we still kind of glossed over a point. What is a wave then? we've said that something's moving from left to right, and we just say, oh, the wave's moving from left to right. That's a little bit vague, isn't it? What do I mean by what is the wave then? If I've identified the fact that it's not the string itself, what is the wave? When we think about it, it's the shape, isn't it? I'm watching this hump moving from left to right, and this one, or this trough moving from left to right. Sorry, I shouldn't say hump, that's the peak. We could say the peak. Okay, peak and trough. And so it's the pattern that's moving from left to right, or we could call it the information that is moving from left to right. And we know that waves are used to carry information. So the shape of that of the peak and trough, like how close they are together, or how far apart they are, or how many there are. Like maybe you might have a wave signal that does this, and then has a break, and then does this, and that could be used to transmit some information if you had a computer to translate it into information. You can also say it's transferring energy. So you could talk about usually what they want is the wave propagation or sometimes energy, but I have seen them talking about information before. So, but this when the oscillation is perpendicular to the propagation, so we can imagine the propagation going down and the oscillation go that way. It doesn't have to be. It can be any direction, of course. It could be going in and out of the board, in and out of the paper. But the point is, they're always perpendicular. When that happens, then we are describing a transverse wave, and I still haven't given myself enough. Transverse wave, and if you write the T like that, it helps you to remind you what type of wave that is. The one that there are types of waves like sound that the oscillation is parallel to the wave propagation. So the air particles are moving forwards and backwards, and then causing a compression and a rarefaction. Rarefaction is when it stretches out. Compression is obviously when it squashes up. And when it's parallel like that, these two directions are parallel, we would say that that's a longitudinal wave. Now, that wasn't the types of waves wasn't on the list, but I thought I'd cover it just in case. So, things that were on the list were amplitude, frequency, wavelength, and I think maybe time period is on the list as well. So let's cover those. If I were to pause this, I can actually measure the wavelength by measuring the distance between any two identical points. So remember, we are measuring, we're transmitting information, and the only information that we're transmitting inside in here would be within the wavelength, because after that, whatever pattern that we're going to be sending it just repeats itself. So the distance between two identical points, between the peak and the peak, or the trough and the trough, we call that the wavelength. And because it's just a distance, it would be measured in meters or centimeters. The standard unit is meters. Next, so that's wavelength. Next would be amplitude. Amplitude is how high up the wave is. So how strong each oscillation is. So it started. You can see this dotted line. This is where the wave would have been. This is where the string would have been if there was no wave being sent across it. So how much has it differed from that point? So it would be this distance here. Now, of course, if we didn't have a reference line, and it's a bit frustrating, they called that reference line. I'd like to turn off that one really to demonstrate what I mean. So you can imagine a wave just being drawn like this, and they might say to you, I mean, the biggest trick question I've noticed is that it's a water wave on something like this, and they might say, maybe the height, maybe that might give you the height from here to here, or anyway, the point is, you should be measuring from the middle point to the top, so this distance here. And that's because the water would have been at that middle point. Okay, so it's how much it's differed. So the amplitude is again going to, well, if it's like this kind of wave would be, you'd measure the amplitude in centimeters, but it depends what's differing, depends what's changing. In this case, the thing that's changing is it's the height of the string. In that case over there, the thing that's changing is the level of the water. But in a sound wave, the thing that would be changing would be the pressure of the sound of the air. Or in electromagnetic wave, the thing that's changing is the electric field and the magnetic field, and so on. So the amplitude is basically defined as the maximum difference that in the thing that is changing. So the maximum difference in between from the halfway point to the maximum difference of, say, air pressure or height of the string or height of the water or whatever it might be. So that's amplitude. Usually they'll give you something much more simple like what we've got here. So in this case, you'd measure the amplitude in meters or centimeters again. So we've looked at amplitude, we've looked at wavelength. What about frequency? Frequency is how often this goes up and down, and it would be the same as how often the things go up and down, the beads or the air particles or whatever else that is moving back and forth. The frequency is how often it does that. More specifically, is how many times per second. So the frequency, let's see if can I get a thinner pen? Pen, no, okay, fine. So the frequency is waves per second. That's what frequency means. It's the amount of waves per second, and the unit for that is hertz. So the frequency we've looked at, wavelength is always going to be a distance. Amplitude could be a distance. It might not be. It depends what type of wave it is. Frequency is always measured in hertz. It's always the amount of waves per second, or the amount of all the oscillations per second. So if you imagine something, let's imagine a child on a swing going back and forth. And that child, we could say, or the swing is oscillating. That would also have a frequency. It's how many times it goes back and forth. Let's imagine that the child goes forward and backwards, and it takes a total of 2 seconds to go back and forth. What would be the frequency then? Maybe you can pause the video and have a think about that. It takes 2 seconds to go back and forth. What would be the frequency? So, if you pause the video, the answer will be that if we want to know how many oscillations in 1 second, it would be half an oscillation, wouldn't it? So the frequency in that case would be 0.5 hertz. So, what is this measurement that we talked about at the beginning then, the 2 seconds? What's that? 2 seconds is what we call the time period. Time period is a symbol capital T, and it refers to, so the time period, or often just called the period, it's the amount of time in one wave, or we could say the seconds per wave. So obviously it's measured in seconds. So notice that the frequency is the waves per second, but the time period is the seconds per wave. So they are sort of opposites of each other, aren't they? And because they totally depend on one another, there is a formula that relates the two with no other variables in them. So time period can be calculated by 1 divided by the frequency. And in the same way, the frequency can be calculated by 1 over the time period. So we've covered wavelength was the distance between 2 points. The amplitude was the strength of each oscillation. In this case, it's just the distance from the middle point to the top, and that's usually the case. I don't think I've seen a GCSE question where they've asked you to calculate the wavelength of a sound wave that I can recall. But you're going to have to look at questions on a case-by-case basis and just kind of apply understanding to what I've just said there. And then we have the frequency is the amount of waves per second, or the amount of oscillations per second. The time period is the amount of seconds per wave, or the amount of seconds per oscillation. So obviously the child on the swing wasn't a wave, but in that case it would be the time period would be the seconds per oscillation. So maybe I can just take a snapshot of that screen, and we can put that on the whiteboard. If you don't know about this tool, I would recommend familiarizing yourself with it. It's called the snipping tool. It's free with most Windows. Well, I think maybe all Windows has it actually. I didn't want to do that. Can I undo this? I have to. How do I? Clear screen. Cool. Okay, and I think cool. So let's just so basically when I took a snip of that screen, I just press Control V, and it pastes it hugely. So I'm just going to shrink that down. I'll put the video next to that as well. So let's just recall this. So this isn't very good, is it? Frequency equals 1 over time. No, it doesn't. It equals 1 over time period. What does just... Nobody's going to really know what just time means, is it? Are they? It's equal 1 over time. That's not a very good checklist at all. Okay. Time period. I didn't talk about wave speed. You can calculate the wave speed by just multiplying the frequency and the wavelength. I could go about proving why that is the case, but we won't do that in this video. The period of a wave is the time it takes for one wave to pass a fixed point. Yeah, the amount of seconds per wave, we said that. Wavelength is a point between from one wave to the same point on the next wave. The bigger the wavelength, the more stretched out the wave is. Yeah. I don't know about the idea of stretching out a wave, but that's fine. The amplitude is the height of the wave from the rest point to the top of the trough. Okay, it should say top. No, that doesn't make any sense. A trough has a bottom, not a top, doesn't it? So, top of the peak. So let's just cross that out. Peak. But you could go down to the trough, right? So in other words, if we have this wave like this, that is also the amplitude there. Okay, that's the amplitude, but so is that. That's also the amplitude, and that is not the amplitude. That would be 2 times the amplitude. Frequency of a wave is the number of waves that pass a fixed point per second. The higher the frequency, the closer the waves are together. Yes, for one, if we're talking about the same type of wave. However, so you could have a high frequency, fast moving. So if you imagine we've got, in fact, maybe I can go back to the simulation. Let me clear this now. I've taken a picture of it. Can I clear it? Can I just clear it? Oh, if I do this, then clear screen. Yeah, cool. So if we press play again now, what we can do is we can change the speed of this wave by changing the tension. So when we have a low tension, then what happens? The wave travels more slowly, and you can see that what happened is the waves got closer together. Now, I didn't change the frequency, did I? So it's not really true to say that the frequent that change in the frequency puts them closer or further apart. It usually does, but it depends. Mind you, again, it could be one of these checklists that are basically very close to just the answers to the test. I don't know. So in other words, if I wrote a question, if I drew some graphs of waves where the x-axis is time, and I was measuring how something is changing over time, like let's say I was just measuring how the activity of this particle here changes over time, I would end up drawing something which looks just like a wave. In fact, if I monitored how that child was swinging, the child started off at the middle point maybe, and then went forwards, and then backwards, and then forwards to back there again, and so on and so forth. And we could measure the distance at each particular point and plot it on a graph. It would also produce this sort of sinusoidal pattern, this wave-like pattern. So if that's what the checklist is referring to, then in that case, then yes, a high frequency wave, the diagram on a graph would be close together, because that's what frequency means in that case. But if we're looking at what the wave itself looks like, it wouldn't necessarily be close together, as I've just demonstrated here. I didn't change the frequency, but they've got close together. And the reason for that is because the wave is now traveling more slowly. When I change the tension back to high, the wave travels more quickly. The frequency stayed the same in each case. The frequency is staying the same, but the wave, because it's now it's traveling more slowly, it's able to, in the same period of time, it's able to get the waves close together, because the pattern is not traveling from left to right as quickly as it was earlier on. All right, I think I've covered everything I can there. So yeah, I'll stop that video there, and hopefully you'll find that helpful. Cheers, bye.